what's going to be today about? So for a lot of people might have thought of it as like Epsilon-greedy method. We're going to talk a very naive solution for the reinforcement learning problem, followed by applying like very typical dynamic programming and then the Monte Carlo approach. And then we're going to talk about Q-learning and Sarsa. And the reason we do it in this order is because if you see for Q-learning and Sarsa, they're going to combine dynamic programming and Monte Carlo-based approach. They combine it together. So you're going to see, okay, this is how Q-learning is, and this is how dynamic programming is, and this is how the Monte Carlo approach is. And then you're going to show you how these two are then combined to make Q-learning. So for traditional reinforcement learning, traditional supervised learning, what happens is you have some labeled data set. You have some data sets like I have apples and have bananas, and then you train your model, and then your model gets like some separational hyperplane, or it gets some decision rules. And what happens, you can give him an unlabeled data point, and it's going to tell you, okay, this is a banana or this is an apple. I think who did this type of machine learning before in his career? Yeah, so pretty much everyone. And what's an alternative or a different problem? Like sometimes you don't have labels in your data, right? You don't know what is what. You don't know if it's good or bad. You just maybe have some general idea. There's like some groups which are more similar and some groups that are less similar, but you don't really know. So what you would do is do some kind of unsupervised machine learning. So you have like some kind of unlabeled data. Like you see, you have some cats, some fruits, and then you train your model. And here the model spits out like some kind of clustering or dendrogram. Like say, okay, he puts the two fruits pieces together, they're kind of some more similar, and says, okay, the kind of the outlier is kind of the cats. So what happens in reinforcement learning? So the way you can think about reinforcement learning is that you want to build a general artificial intelligence. So the artificial intelligence here, or the model, we call the agent. And the agent interacts with some kind of environment. And the environment here in this course is going to be mostly video games. But they don't necessarily need to be video games. And the beauty of this is that you have two parts, right? One part is like the reinforcement learning part, which is like the models and the algorithms, and they're very decoupled from the environment. And then the environment part is like, how do I create the environment, right? And there are a lot of tricks. If you look at the applied reinforcement learning, where you have to do like to put your real world problem in this kind of environmental system. And how does the agent interact with the environment? So the agent can perform some action. And then the environment sees, okay, you perform this action, and it will let the agent know, okay, what's going to be your reward and what's the next state of the environment. And this relationship between the agent and environment is kind of an iterative relationship. So it's always the agent interacting and getting information from the environment. And then based on that information, it acts again. And until like the environment says, okay, this episode or this run of this game or whatever is finished. But there are also episodes or games or environments that are unlimited. They can just go forever. And then when you do the training there, you can say, okay, after 500 steps or 600 steps, I just stop. And these are 4 central reinforcement learning concepts which we will learn today. So number 1 is like the policy. So the policy is the decision or the system that gives the AI, how does the AI decides the action based on a state. Say if I'm in state A, I do action B. If I'm in state C, I do action A. If I'm in, say, state B, D, I do action G, and so on and so on. And these policies, they can be like fixed deterministic. Say, whenever I am in this state, I do this action. But these policies can also be statistic, like distributional. Say, okay, I do this action with this probability and do this action with that probability. The second most important part is the reward. So the reward is what the agent tries to maximize. So you do an action, and the system tells you, okay, you do really well, I give you like a reward, or you do really bad, I give you a very negative reward, or if you do really well, I give you a very positive reward. And the third big concept is like the value function. So the value function just tells the model how advantageous a state is, or a state action pair is, if it's the state action value function. And for most of the machine reinforcement learning, this is going to be model free, but there are also model-based reinforcement learning where you try to simulate the model. So the agent also has a simulation of the environment, which they also try to optimize. So, further ado, let's play a game. So, I think most of you are familiar with it. It's got two-armed bandits, and I think we're going to play it. So we have a bandit has two arms, and you're going to pull a lever, and you're going to collect some money. And I think we're going to play some rounds to warm up, to give you some idea. And you can say left, you can shout left, or you can shout right, and I will let you know your reward. Come on. Left. 1. Right. 0. Left. 1. 1. Left. 1. Right. 0. Right. 0. 1. Okay, everybody. So, want to go in your breakout group? You want to discuss, and you want to think for a few minutes. What your next 10 pulls, right? And we want to talk with your teammates and in your breakout group and your people online. Please think about it. Just say what would be the next 10 times, and then we have a poll. It was just posted in the general chat. You're gonna select. You can vote how many times would I pull left or right, one of those two things. So you're gonna say, okay, for my next 10 pulls, I'm gonna pull left 10 times. Well, I think we finished. Everybody voted. So we got 9 votes. So if you say, I hope it was everybody clear. You say how many times you pull left. So if you say you pull left once, it means you pull right 9 times, right? So left gives you 100% of the time give you like $1, but say the right in 1 in 10 gave you like $100. So you might have thought what happened is a lot of people voted, oh, I would put always the left, right? And this is what happen often in reinforcement learning. It can be a problem in reinforcement learning. It's like you get converged like to a local optimum, right? It wasn't the best policy, but it was a good policy. You got some rewards, right? But it wasn't the best one. Best one is just keep pulling R. Because this is like Bernoulli. So for those who want to understand it better, it's like a Bernoulli process, right? So you have 1 in 10, so expected value would be after 10 pulls would be 100 or 10. So they're roughly the same, actually. Okay, so we have a k-armed bandit. So what happens, we have, say, k-armed is like you have infinite many of levers you want to pull, like not 10 or hundreds, but infinite amount of ones, right? And the problem is now, how do you come up with an algorithm or an idea that can find the optimal policy, the optimal way of finding which arm to pull? And what you see, you have a selecting of infinite actions and infinite rewards. And for those who want to say it, one thing is this problem. One of the key components are missing. Anyone noticed?
The budget. Like how much?
No. Yeah, kind of. But we were talking about the core concepts in the reinforcement learning. The policy is what we are trying to come up now. It's the state. It's a stateless event, right?
Why is it the state inside?
Because it's stateless. You always have the same set of actions, and you don't have a different state, right? Your reward doesn't depend on your state. Your reward doesn't prevent from your previous reward, right? Or any other dependencies, right?
You only have one state, and there's no transition.
Yeah. Without.
You say it is a stateless.
Okay, technically you're right, but for calculating the optimal policy, the state, the reward is independent from the state, right? So it kind of falls out. So as you notice, we have like an action, it's like a kind of response and control, and Like it can be also these actions itself. They can also be discrete, like yes or no, or left or right. They can also be continuous, like oh, I want to move this servo by 10% and the other servo by 20%. If you say think about a robot like an arm, and then every finger has multiple like servos, like wheels where you can turn and twist. And or say you have a blast furnace, right, and you want to increase the temperature or you want to decrease the temperature, and pretty always your complete set of actions is always known. So the agent knows what action it can do. It's just not like a hidden state. And we have a reward, which is like your gain, your payoff, or your cost, right? So say if it cost me say $10 a minute to run this cluster, then I want to kind of minimize the cost, right? To get negative rewards, so the agent will be trained to make short sequences, right? And the reward itself is like immediate after each step. You see, you pull a lever and you get your reward. And so what are the strategies people can come up with? This. So I don't know they're here. So let's say you want to pull every lever n times, and you select the lever with the best reward. Anyone want to say what do you think about this idea? Or if people online, you can just post into the Slack. And everyone and one of the TAs, let me know. What do you think about this idea?
With that, then we're assuming that whatever happened in the past has an influence on what's going to happen in the future. Like, say the results are just like random, so that's probably not given like a lot of information.
Yes, to some degree.
Isn't this technically like something like brute forcing, but then like there's no this assumes that each reward is going to be kind of the same as before, right? Like there's no point of maximizing this step, right?
So kind of, yeah, you brute force it. So I mentioned in the case we have like infinite arms, right? Say if your action space is very, very large, it's going to take you a very long time to sample each action space, right? And the other problem is rewards can be very, very sparse. So maybe you sample a certain state 100 times, you visit a state 100 times, you don't get any rewards. So let's say, okay, let's come up with a different strategy, right? It's a little bit better. So what we see here is like a human trying to come up with a policy, right? You're trying to come up with a policy how to find the best lever to pull. So let's say we pull the lever n times randomly. We take us randomly, we pull the levers n times. Say we have 100 levers, we just pull 500 levers randomly, and we average the reward we get. So what's the problem? Okay, so I mentioned two problems, right? One was like, oh, it's like a very large space. This got addressed. But what the other problem? The reward can be very sparse, right? So you don't really know at what point you need to stop the pulling, right? Because so let's say take this policy and we enhance it by another step to help you with this kind of sparseness. So we say we're going to pull the lever n times randomly, and we select after n times. We say, okay, after 1,000 times, we're fairly confident these are the good levers, right? And we say, okay, we keep pulling those. But say every 100 pulls or every 20 pulls, we just randomly picked another lever. So this way, you kind of optimize towards a local optimum very quickly. And if there's a kind of global optimum over a very long period, you will find it as well. Because say you run infinitely long this sequence, you will find the best lever. So if you have any questions, let me know at this point. Online also, please. I have this like open on my phone, so I try to look on this chat from time to time for those wondering why I always bend over. So this is a little bit what I just said, just more in a kind of mathematical equation part. So what we're trying to estimate is like the action, the value of the action, the expected return. And a way we can measure this expected return of a certain action is say, okay, we just average it. Right? We do the action 100 times, and we just average over it. And this works if you don't have any state dependency, right? So if you have a state dependency, of course, this equation, this A, also becomes under dependent of state S, like the action of A given state S. And you're going to see this a lot in reinforcement learning. So you're going to see, okay, it's just the summation, the average of all the rewards from step, right? But what's then? We can just say we take one reward out. We look at the previous step. And if you go through it, what you see is like, oh, the reward of the next step, like the expectation reward, the expected reward of the next step, it's just the expectation reward of the previous estimate plus the reward we get from the next one. So we see we have our new estimate. We take our old estimate, and this is, you can think of a bit of a step size. And this is like our reward, like the difference between what we estimate and what is the actually real reward. And this is very similar to rudimentally also the idea behind Q-learning. And this is what the Epsilon-greedy algorithm looks like. So we're now going to code this together in Python. And if you have any questions now for the theory, please let me know now.
Can you go back to the last slide? So, sorry, the one before as well. So, yeah, I understand the first three equation, but then when you said n minus 1 is now nqn,
Yes.
can you elaborate on that more, if possible? For the fourth equation.
For the fourth equation, you mean this one?
No, that's the third, right? Yeah.
This one?
Yes.
So it's like 1 divided n times n qn. You take the n out, and then it's qn plus 1n of what's inside.
Yeah, but how did I understand?
You understand? Like
the third to fourth is the.
So you say this 1n is like re from e to 1, right?
Yep.
There's nothing than rn plus 1 negative, right?
Yep.
And then I say, okay, n minus 1 times 1 divided by n minus 1 equals 1, right? But this is qn, right?
So this is a known equation, right?
Yeah, this is a known equation. So you take this and you make it to n times qn minus qn. And then you solve it.
Okay. So this acts as the previous state.
Yeah.
Okay.
So,